Welcome to UGC lecture series Linear Integrated Circuits. In this lecture we are going to continue the second order filter, its transfer function and design of filter. Next is band pass filter, its transfer function and design of the band pass filter. In the previous lecture we have derived the transfer function of the second order filter. Here if you substitute y1, y2 as 1 by r and y3, y4 as c by s, cs, it is the second order low pass filter. So now we are going to substitute the values in order to get the transfer function of the second order low pass filter. Then only we can come to know that if the order increases, how the increase in the frequency, what is the change in the response of the filter. So if you substitute the value now, v0 by vi is equal to y1, y2 is 1 by r. So, a by r square divided by here 1 by r square plus y2 is 1 by r, y3 is cs. So, cs by r into 1 minus a plus y4 is cs, y1 is 1 by r plus 1 by r, another 1 by r. So, it is 2 by r plus y3 is cs. If you take LCM, it is csr. So, we want to cancel out this r square in both the denominator and the numerator. So, I am taking 1 by r square as common, 1 by r square. So, I have 1 plus, if I take 1 by r square common, I have to multiply r in the numerator of the second term. So, you have CSR minus, multiply inside this CSR minus A into CSR, A into CSR. Next plus 2 CSR, the next term is CSR already present. So, if you multiply CSR, it will be C square, S square, R square. So, this is the equation we are getting. So, now R square and R square will get cancelled and simply the equation is now A by 1 plus, here you have CSR, CSR, again CSR. There are 3 terms. So, you can take the CSR out. So, you have 3 minus A, 3 minus A plus C square, S square, R square. So, this is the transfer function of the second order low pass filter. Generally, for any system, it may be electrical system or a mechanical system or a hydraulic system, the transfer function which is given as, this is in general, which is given as A W H square divided by S square plus alpha W H S plus W H square. So, here this W H is the frequency term and this alpha is the damping coefficient. So, now if you relate this and if you relate this equation 1 and 2, you can come to know that the WH is 1 by RC. If you relate this, you have, okay, here it is plus, if you take plus CSR, then you have 3 minus A, 3 minus A. And so, here if you relate these two equations, you have WH is equal to 1 by R and alpha is equal to 3 minus A. Alpha is the damping factor. And before that, you have to make this the numerator as A naught only. A naught is equal to A here. So, if I consider this V naught of S by Vi of S, the general equation of any system, then I am taking this A naught in the numerator. I am dividing this equation by WH square in both numerator as well as in the denominator. So, I have S square by WH square plus alpha S by WH plus 1. So, now if you see the equation and relate the equation, you have WH is equal to 1 by RC and alpha is 3 minus A, and if WH is equal to 1 by RC, it is 2 pi f actually. The omega is 2 pi f. F is equal to 1 by 2 pi RC. This equation, if you take the magnitude or the mod value of this transfer function, now it is, we know you have to substitute S is equal to j omega, then only you will have the real term as well as the imaginary term. So, here if S is square is j square omega square, you have j square as minus. So, omega square by omega h square plus alpha j omega by omega h plus 1. So, you have only one imaginary term and two real terms. So, if you simplify this, you have A naught in the numerator divided by 1 minus omega square by WH square plus j into alpha omega by omega h. So, if you take mod for this value, A naught divided by root of real term square plus the imaginary term square. The real term square is 1 minus omega square by omega h square. 1 minus omega square by omega h square the whole square, this is the real term, plus the imaginary term is alpha omega by omega h the whole square, this is the imaginary term. So, this is real term square plus the imaginary term square, and in the numerator it is A naught, or simply you can consider this as A. And now if you expand this and substitute this alpha is equal to 1.414, and this damping factor represents the damping factor of the Butterworth filter. We have discussed in the previous lecture that all the audio filters are the Butterworth filter, since the response of the Butterworth filter for this damping ratio is flat for the pass band. And if you substitute this alpha square with the 1.414, it is actually root 2, and if you expand this term, root of, it is A minus B the whole square. So, A plus B square, A square plus B square by omega square the whole square minus 2AB. And here if you substitute this alpha as 1.414, this is root 2. So, root 2 square and omega by omega h the whole square, you will have the terms, these two will be getting cancelled out, and finally you have A naught by root of 1 plus omega by omega h the whole power 4, and this is generally written as root of 1 plus omega by omega h the whole power 2 into n. This n stands for the number of order. If n is equal to 2, then this will be 4. This will be 4. If n is equal to 3, then this power term will be 3 into 2, 6. In that way, if you increase the order of the filter, then this formula will be 2 into 1, 2 into 2, 2 into 3 and so on. So, this is the transfer function of the second order low pass filter. And if you want to calculate the transfer function of the second order high pass filter, what you have to do is, in the normal transfer function, this is the general transfer function of the second order filter, you have to replace this y1 y2 as Cs and this y3 y4 as 1 by r. Just you have to replace the passive component terms and calculate V naught by Vi and put S is equal to j omega, and finally you will be getting the equation we are going to discuss about now. So, in the normal general equation, you substitute these values, you will be getting h of s as this a naught s square by this term. And if you put, so previously we have represented the cutoff frequency as omega h for low pass filter, and here it is omega L for high pass filter, it is given as 1 by RC. And if you replace this as 2 pi f, it is f is equal to 1 by RC. In this case, the lower cutoff frequency f is equal to 1 by 2 pi RC. And this equation is simplified as, so this s square is cancelled out in this equation. So, you will be getting as 1 plus 3 minus a naught omega L by s plus omega square L square by s square. So, if you put s is equal to j omega, then you have 3 minus a naught is equal to alpha. If you alpha equal to 1.414, if you substitute this value, similarly in the case of low pass filter, you have this term a naught by root of 1 plus FL here, this is the lower cutoff frequency, divided by 4, f the whole power 4, in this case also 2 into n. So, this is the transfer function of the high pass filter, which you can solve by yourself. And the next topic is the band pass filter. The band pass filter, which is a filter which pass the frequency of signals of the specified band and attenuates the signals outside the band. There are two types of band pass filter which are classified as per the figure of merit or the quality factor Q. They are narrow band pass filter if the quality factor is greater than 10, and wide band pass filter if the quality factor is less than 10. If Q is given as the center frequency f naught divided by the bandwidth. So, the bandwidth is the difference between the higher cutoff frequency and the lower cutoff frequency, and the center frequency is calculated as root of the higher cutoff, the product of the higher cutoff and the lower cutoff frequencies. So, if the bandwidth is low, then you will have a greater Q factor, Q greater than 10. So, it is a narrow band pass filter. If bandwidth is high, it is a wide band pass filter. In that case, you will have a Q factor less than 10. So, how will you construct a band pass filter? Single first order band pass filter is, we know the response of the frequency response of the band pass filter. Take frequency along the x axis, frequency of the input signal along the x axis, gain along the y axis, and the band pass filter is, first you have a stop band and next pause band and next is stop band. So, this is the ideal response of the band pass filter. So, first if you want to stop the frequency or attenuate the frequency of the signals, then after the cutoff frequency 1, it is going to allow the signals up to the cutoff frequency 2. So, between these frequencies all the signal is getting passed through the filter. Beyond these two cutoff frequencies, the signals are attenuated. So, this filter response is actually, if you divide the filter response, this is actually the first stage is the response of the high pass filter and the second is the response of the low pass filter. Because in the high pass filter, initially the frequency signals are attenuated, and after the lower cutoff frequency only the signals will get passed through the filter. So, this is FL. And for the low pass filter, initially the signals are getting passed, the lower frequency signals are passed and the signals outside the lower cutoff frequency is stopped. So, this frequency is higher cutoff frequency, this FC2. So, this is the bandwidth. The difference between the higher cutoff frequency and the lower cutoff frequency is the bandwidth. So, only the frequencies between this lower and higher cutoff frequencies is paused. The frequencies outside this band is attenuated. So, now as per the frequency response of the filter, first you construct the high pass filter, then the output of the high pass filter is given as the input of the low pass filter. So, cascading the high pass filter and the low pass filter will give you the band pass filter. So, high pass filter, you have the capacitor in the input arm, the resistor in the shunt arm. Say this is R, this is C, this is Vi. Here the resistor is grounded and given to the negative terminal, the feedback resistor is given to the negative terminal from output. So, this is the high pass filter. If the output is taken as the input of the low pass filter, and we know that the low pass filter has the resistor at the input and capacitor at the shunt, and which is given to the positive terminal of the operational amplifier, and negative terminal is grounded through the resistor, input resistor, and feedback is given. So, this is the circuit of band pass filter. So, now if the question is design a band pass filter for the lower cutoff frequency as 200 hertz and higher cutoff frequency as 1 kilohertz, for the gain A is equal to 4. If this is the design, then you have to consider that the gain given as 4 is actually the product of the gain of the amplifier A1 and the amplifier A2. So, A1 has the gain 2, similarly A2 has the gain 2. So, if you multiply these two gain, then you have the entire gain of the band pass filter as 4, and we know the formula 1 plus Rf by R1 in either case. So, you have to assume the value of the input resistor R1 as always 10 kilo ohms and find out the value of the resistor, feedback resistor Rf. And this lower and higher cutoff frequencies are for designing the filter stage components. So, this lower frequency is for the high pass filter. So, 200 hertz is given for the high pass filter. So, FL is equal to 1 by 2 pi RC. Here C is assumed to be 0.1 microfarad and calculate R. It is given as 200 hertz. So, calculate R from this, put the values in the high pass filter, and similarly FH is given for the low pass filter. Again the same formula, FH is equal to 1 by 2 pi RC. It is the same formula. C is assumed to be 0.1 microfarad and R is calculated. These values are given for the low pass filter. This FH is given as the 1 kilohertz, 1000 hertz. Design a band pass filter having FL 400 hertz and FH 2 kilohertz, pass band gain of 4. Find the value of the quality factor of the filter. So, FL is 1 by 2 pi RC, which is for the high pass filter, which is given as 400 hertz, for which C is assumed as 0.1 microfarad. Calculate R, and FH is 1 by 2 pi RC. This is for low pass filter, which is given as 2 kilohertz. Assume C as 0.1 microfarad, calculate R. And A is given as 4, A1 into A2 is 4. So, A1 is 2, A2 is 2, which is given as 1 plus Rf by R1. R1 is assumed as 10 kilo ohms. So, this is the design. Calculate the values of R and C of the filter stage as well as Rf and R1 for the gain of the amplifier. Next is cascading the filters. When cascading the filter circuits together to form the higher order filters, the overall gain of the filter is equal to the product of each stage, as we have seen in the band pass filter. And the band pass filter is actually the first order filter. If you want to increase the order of filters also, we will be cascading the filters. In that case, the product is, the overall gain of the filter is equal to the product of each stage. For example, the gain of one stage may be 10 and the gain of the second stage may be 32 and the gain of the third stage may be 100. Then the overall gain is the product of all the gains, which is equal to 32,000, which is shown here. So, this is the gain of the first filter, and this 30 dB is the gain of the second one, and 40 dB is the gain of the third filter. If all the three gains are multiplied, then which gives you the overall gain as 32,000, and if it is calculated in dB, it is 90 dB. Cascading the active filters. If you want to have the first order filter, for the first order filter, we know that we have to connect a single set of R and C component for the filter stage, which produces the roll off rate as 20 dB per decade. And if it is a second order filter, we know that another set of R and C pair is connected in the filter stage, which produces 40 dB per decade in the frequency response. And in the third order, first stage filter and the second order filter, actually the first order filter is cascaded with the second order filter to produce the third order filter. In that case, another 20 dB decade is dB per decade will be added to the response of the filter. So, can you guess for the fourth order filter how the circuit will be? It is the cascading operation, cascading of second order filter with the another second order filter. Then the roll off is 80 dB per decade, another 20 will be added to this in the frequency response. And fifth order, it is similar to the third order. You have a first order stage and which is cascaded with the second order filter and then another second order filter, which has the roll off rate as 100 dB per decade in the frequency response. Similarly, it goes on. So, in order to cascading the filters or in order to increase the number of the filters, we have a first order filter and the second order filter. So, these two filter combinations are added to get any order filter in the. So, this is the transfer function of the higher order filters. This is the second order transfer function, A01 by Sn square plus alpha 1 Sn plus 1. So, this here the Sn is the normalized frequency, alpha 1 is the damping factor. So, this is the second order response and this is another second order response. So, if the two second order filter is cascaded, then this is the transfer function of the entire overall transfer function of the circuit. So, here A02 by Sn square plus alpha 2 Sn plus 1. Here the gain is different and the damping factor is also different from the first second order filter. And if you want to make it as fifth order filter, you have to add a first order section. So, in this case the transfer function for the first order is A0 by Sn plus 1. So, here again the gain of the filter is different. So, in this transfer function we come to know that the damping factors are different and the gain of the filters are different. So, these are the normalized Butterworth polynomial in the denominator of the transfer function. So, this first column shows that the order n, and these are the factors of the polynomial. If you look at the order 1, the factors of the polynomial says that it is 1 plus Sn. See here, this is the denominator term for the first order section. So, it is Sn plus 1. For the second order, it is the same, Sn square plus alpha 1 Sn plus 1 here. Here just the damping factor is different, but the polynomial is the same, Sn square plus Sn plus 1. So, for the second order, if you see this is Sn square plus Sn plus 1. For the third order, we know that we will add a first order filter with the second order filter. So, this is the denominator of the transfer function of the entire filter, Sn plus 1 into Sn square plus Sn plus 1. Similarly, if you increase the order of the filter, for every odd number of orders, you have Sn plus 1 multiplied with the second order filters, and for every even numbers, you have even number of the order of the filter, you have this kind of polynomial, Sn square plus S plus 1 with its own damping coefficient. So, these factors of polynomials are the Butterworth polynomial only we have discussed, since it is the filter used for the audio range of frequencies. So, in this class we have designed a second order filter for the frequency 2000 Hertz, for which we know that the frequency of the filter is f is equal to 1 by 2 pi RC. So, here we have derived omega is equal to 1 by RC. Here omega h is equal to 1 by RC. If the frequency is given as 2000 Hertz, what we have to do is, you make this f is equal to 2000 Hertz, and normally we will assume the capacitor value as 0.1 microfarad. So, R is calculated from the frequency value and the capacitor value, and the gain of the filter actually it is derived from alpha is, now the alpha is 3 minus A naught, alpha is 3 minus A, alpha is given as 1.414. So, from here what is the gain? So, A is equal to 3 minus 1.414. So, from this the gain of the amplifier is derived, and the gain is 1 plus Rf by R1. This is the second order Butterworth low pass filter having upper cutoff frequency of 1 kilohertz. Here we know that f is 1 by 2 pi RC, it is given as 1 kilohertz. Here C is assumed as 0.1 microfarad, and calculate what is R. And we know that alpha is equal to 3 minus A naught, which is given as 1.414. From here what is A naught? That is the gain of the filter. A naught is equal to 3 minus 1.414. So, you have to calculate it, and this is equal to 1 plus Rf by R1, 1 plus Rf by R1. From this you have to calculate the values of Rf and R1. R1 is actually 10 kilo ohms, and then what is Rf you can calculate from here. So, if it is for 1 kilohertz, you are doing these steps. If it is for 2 kilohertz also, the same steps are being followed. And next is list the types of the band pass filter. We have discussed in this lecture about only the wide band pass filter. We have narrow band pass filter also, but we have discussed only the wide band pass filter. Construct a wide band pass filter. How will you construct it? It is actually the cascading of high pass filter with the low pass filter. Discuss the frequency response of the band pass filter. So, in this lecture we have discussed about the second order filter, its transfer function, design of the second order filter. Band pass filter transfer function of the bandpass filter and design of the bandpass filter. These are the references. Thank you.